Now that we've introduced Neptune as a tool to aid synthetic biologists in designing microfluidics for various experiments, let's follow an example researcher looking to do just that. Our story begins with Dr. Ali, a synthetic biologist with the simple yet exciting idea of creating a microfluidic that will help him characterize the expression of a novel genetic part when variable levels of inducer are present. He envisions a chip will look something like this, with an input for cells suspended in culture media, as well as an input for his inducer, which is valved to control when the inducer will be flowing through the chip. Dr. Ali includes a third valved input for testing how his genetic part will react to multiple inducers. All three of these inputs will move through a snaking serpentine mixer, then over a line of cell traps, and finally through the output of the chip. Keeping the idea of his microfluidic experiment in mind, Dr. Ali sets out on finding a design and fabrication flow that will work for him. Dr. Ali knows that his experiments will be very iterative in nature. He will be making adjustments to the dimensions of his microfluidic components often to find the perfect match for his experimental protocol. In fact, there are nearly infinite combinations of parameters that Dr. Ali can think of that could improve the performance of his design idea. For instance, what if he finds out that his original cell traps are too thin and don't properly catch his cells, or that his channels are too wide and too much fluid flows through the chip, or even if his mixtures aren't long enough and he needs a more homogeneous fluid flowing over his cell traps. With all these parameters and more in mind, Dr. Ali decides that he needs a microfluidic platform in which he can rapidly prototype his device idea to make it perfect for his needs. Lucky for Dr. Ali, the Neptune microfluidic creation system streamlines the iterative process like no other design and fabrication flow.
Now, to create his microfluidic device, Dr. Ali has two options. He either builds the device himself in the lab, or he can order the device from a manufacturer that will specialize in chip fabrications. Let's say Dr. Ali decides to manufacture in the lab using the most common method, photolithography. First, Dr. Ali will need to fabricate a mold for his chip using devices like a spin coater and a mask aligner. Then he'll need to prepare a substrate for his chip with a vacuum mixer, and he'll need to incubate the chip. Finally, Dr. Ali will need to create multiple layers of his chip, align these layers with a stereo microscope, and bond them with a plasma bonder. I should emphasize that this manufacturing process is constrained by incredibly high tool costs at nearly $80,000. This doesn't even include the cost of materials, training, or the time investment. What about ordering a chip? Doing some research, Dr. Ali finds that most manufacturers retail chips at very high costs, averaging at several $100s per batch. Worse off, these chips can take several weeks to be made and shipped to order. This makes experimentation through rapid prototyping nearly impossible.
Introducing Neptune, the simple-to-use, low-cost microfluidic creation tool enabling the rapid prototyping of designs. After choosing and obtaining Neptune, Dr. Ali opens up the tool to a welcoming homepage where he can begin to make his custom microfluidic. He chooses where he wants to store his files and starts a new project. He then names his new project Inducer Expression Chip after the type of chip he is creating and proceeds to Neptune's overview page. This page provides Dr. Ali a cohesive picture of Neptune's capabilities, taking him through the functionality of Neptune at a high level. Starting from scratch, Dr. Ali will go through all steps of Neptune, starting with specify and design. After the chip is done, next up is building, assembling, and controlling his microfluidic chip and control system. Having finished creating his project and armed with a general overview of Neptune's functionality, Dr. Ali moves to step 1 of Neptune, specify.
Now that Dr. Ali has created his project, he can specify his microfluidic chip using Neptune's simple, high-level description of microfluidics, the liquid flow relations. These liquid flow relations, or LFR, consist of the inputs to his microfluidic, the microfluidic components which act on these inputs, and the outputs to his microfluidic. The inputs and outputs are defined explicitly in LFR, while the microfluidic components between them are written as operators. These operators are described in the user constraint file, where each component is defined specifically with tunable parameters for experimental rapid prototyping. For instance, if Dr. Ali experimentally discovers that all of his cell traps are too wide to trap cells, he could change every one of them by editing one value in this file. Recall that, with traditional microfluidics, Dr. Ali would have to individually resize every instance of his components by hand using a CAD tool. When Dr. Ali is satisfied with his LFR and user constraint file, he can translate his high-level LFR into a more detailed description, mint, like so. Much to Dr. Ali's benefit, the few lines of LFR he has written now become scores of lines in this more descriptive description, mint. Dr. Ali will now continue to the design stage of the Neptune workflow, where he can optionally make very precise adjustments to his chip.
Now we are going to go ahead and compile the specification down into what is called a microfluidic netlist file. As it turns out, this is an incredibly powerful way to make a microfluidic design modular. An LFR file, at the most basic level, specifies flow inputs, outputs, and the flow manipulations that happen in between. This means that other parameters, like valve size and channel width, can be tuned to match a specific design case. Dr. Ali can write a single LFR file. He could share this file with his coworkers, and then each researcher could actually take this single design and fine-tune the design for their personal experimental setup. Here you see an editor where we can change the parameters of a mint file. Dr. Ali can edit parameters like the width of his channels or the size of his valves, thereby ensuring his devices work on both mammalian and bacterial cells, depending on the experiments he is running. Now let us compile this design and look at what our final design schematic is. During compilation, Neptune provides a console readout of your microfluidic design validity. If any design errors occur, the compiler will give Ali a warning. In this case, Dr. Ali's design schematic was created successfully. Here we see Dr. Ali's chip with his 3 inputs, a cell trap, and a mixer. This is a complete design schematic, and he can now use it for fabrication. The final design schematic includes SVG files for CNC milling chips, or EPS files for photolithography masks. Now Dr. Ali is going to proceed to build his device.
Now Dr. Ali enters the build page, where he specifies which servo-syringe combinations control his microfluidic chip. There are 3 steps, the first being the specification of volume, indicating the maximum amount of liquid he needs to dispense, and tolerance that needs to be achieved for dispensing small amounts of liquid. Step 2 is choosing the particular servo-syringe combination desired, all of which meet the above requirements. Step 3 is where Dr. Ali maps which combo will be attached to which chip input. The valves are automatically assigned to Neptune's ideal valve control combinations. He can view his custom chip and then get his custom ordering list, detailing all components he needs in order to get his system up and running. They are ordered in terms of electronic, servos and syringes, hardware components, and other optional components. Next up is assembly, a 6-step process. The first step is for Dr. Ali to order the parts detailed in the ordering list already downloaded on his computer. This includes the 3D printer and desktop CNC, which will be used to make other hardware. Step 2 is to make this physical hardware. 3D files are provided to print Neptune's servo syringe mounting system. The files needed to mill out the microfluidic chip are also provided to be used with the desktop CNC that Dr. Ali has already ordered in step 1 above. Step 3 is the connect stage, where Dr. Ali will hook up all servos to the Arduino Mega in the order set by Neptune. These pin numbers are available on the control page with a link provided here. Step 4 is the assembly stage. Dr. Ali will connect the servos and syringes together on Neptune's baseboard and initialize them with the click of a button. Step 5 is the preparation of the microfluidic chip for use. The chip itself is made in step 2 of this page. Here is where Dr. Ali will add ports to the chip and seal it with PDMS. Next is to attach the syringes to the chip through the attached ports as seen here. Finally, step 6 is to use the system. Dr. Ali is ready to control his microfluidic chip. Moving forward, he can share his design on GitHub or reach out to us via email with any questions he may have. He can also visit our website for more information.
After Dr. Ali has milled his chip and assembled his components, he can control his entire microfluidic system from within Neptune. When he navigates to the control page, he can continue working on his current project or switch to another microfluidic design he wishes to control at any time. But for now, Dr. Ali wants to control the chip he has just built. In front of him will be a visualization of his chip, with valves marked with green buttons and dispensers marked with purple. If Dr. Ali wishes to refer back to the specs of each of his servo-syringe combinations that control these valves and dispensers, he can do so by opening the settings page. Before Dr. Ali can operate his microfluidic device, he must first open a serial communication port with his Arduino Mega. To do this, he simply navigates to the serial communication page, selects the correct port which his Arduino is connected to, and presses Open COM. Now, when Dr. Ali navigates back to the control page, he can open and close valves and dispense liquids to his device by simply clicking on the respective buttons and observing as Neptune reflects the state of the physical setup. Whenever Dr. Ali wants to operate the dispensers of his system, he can either send commands by indicating a volume amount to be dispensed evenly over time, or he can gradually increment the output of his syringe using his up and down arrow keys.
Having learned Neptune's controls, Dr. Ali begins conducting his first experiment. As a reminder, his goal is to characterize the expression of a novel genetic part when variable levels of inducer are present. First, Dr. Ali sends through cells mixed with culture to trap the cells in his microfluidic chip. After this, he opens up the first valve, which is controlling the inducer's ability to enter the chip. Second, he flows a blue inducer over trapped cells to induce expression. He then clicks on the first valve again, closing it and cutting off the inducer from the trapped cells in his system. Third, Dr. Ali flows culture mix over the trapped cells to keep them from dying before they express. And that's it. Dr. Ali has then finished his first genetic experiment using Neptune. Here is a close-up of the fluid flow in action. Dr. Ali plans to redo this experiment multiple times with varying levels of inducer in the blue liquid, simply by clearing the chip and using new inducer. Changing the setup is easy. To change syringes out with one another, simply snap out the syringe from its holder and snap another in its place. No unscrewing components from the board, and no mess. Just as Neptune worked for Dr. Ali's experiment, Neptune's hardware is adaptable to a huge number of unique experiments. Ranging from 2 valves and 1 fluid controller to hundreds of both, Neptune can handle the job with only one Arduino. The baseboard is compatible with an emerging standard in microfluidics that is modular and expandable, expanding the reach of a desktop CNC into what typically requires a full machine shop. Should our servos or syringes not have the required tolerance or volume, users can input their own parts. Neptune automatically creates 3D parts to fit them perfectly. Neptune can adapt to the user's specific project needs, providing a wide range of possibilities along precise levels of control, all at a fraction of the cost of conventional fluid dispensing systems.